presentation.
Okay, recording started. Okay.
Okay. So then I would like to start today's presentation about the physics of Andreev bound state in superconducting junctions. This work it was done in collaborated with many people listed here. Especially I have been collaborating with Professor Kashiwa a long time, and also Professor Asano or Gorubo-san, and also Professor Sato, and listed as members in Nagoya University, and Chinese, and also Madrid, Pablo-san in Madrid. So today's lecture, the plan is as follows. And the first part of my lecture is rather fundamental. Start from basics of superconductivity, and then go to Bogoliubov-Dujan equation. So let's start from very basics of superconductivity. So first we'd like to explain very generic form of Hamiltonian, including electron-electron interaction. So if we assume some attractive interaction like that, and if we assume mean field approximation, so-called pair potential or gap function is written as follows. This is a standard BCS theory. So the mean field Hamiltonian can be nicely written in 2x2 matrix form. And after Bogoliubov transformation, we get the answer. And finally, we get that this is an important energy spectrum of quasi-particles. And after diagonalizing Hamiltonian, we get the Hamiltonian. It is so-called mean field Hamiltonian like this. And the important point is that the pair potential delta is self-consistently determined, and the energy spectrum of superconductor has such kind of gap-like structure. So it's similar to, for example, semiconductor or infinite, but the meaning of this energy gap is very, very different. And the physical property of energy gap is very different from that of insulator or semiconductor. So I'd like to mention about this from now more in detail. So before that, today's topic is mainly concentrating on unconventional superconductor. What is unconventional? In strongly correlated systems, pair potential changes sign on the Fermi surface. So quite different from isotropic pairing, Cooper pair is formed between two electrons with different spaces due to strong Coulomb repulsions, like that, D wave or P wave. And then how to express this, like mean field style. So it's possible if we introduce spin degrees of freedom into pair potential, into gap function, it is formally written like that. So the original Hamiltonian is extended to from 2x2 to 4x4. So then it is straightforwardly to consider the energy gap function. And then basically in the presence of inversion symmetry, special inversion symmetry, the parity of Cooper pair is classified into even parity one and odd parity one. And the even parity case, it should be spin singlet to be consistent with Fermi-Dirac statistics. And in odd parity case, it should be spin triplet. And it is conventionally written by using so-called D vector. So after straightforward manipulation, calculation, the eigenvalue is diagonalized, and it is written like that, Ek plus, Ek minus, minus Ek plus, minus Ek minus. So then, first we look at spin singlet case. Energy spectrum is very simply written like that, quite similar to conventional, very simplified BCS theory. Only the momentum dependence appears here. On the other hand, triplet pairing case, spin triplet pairing case is a little bit complicated. If this vector, so-called Q vector, Q is determined by D times D star, if it is 0, it's quite similar. The energy spectrum is quite similar to standard BCS1. On the other hand, if this value is non-zero, it should be modified like this. So this is a so-called non-unitary pairing state. And the most important point of unconventional superconductor is like that. It has a nodal structure on the Fermi surface. So one of the typical nodal structures is line node listed here. Another one is point node. So recently, the physical origin of these nodes are understood based on so-called topological invariant. So I'd like to mention about this topological invariant in the latter part of my lecture. So it is well known that in the presence of nodal structure, the density of state is greatly modified. So around 0, around energy equals 0, in the presence of node, like polar phase, line node, density of state is proportional to magnitude of omega. It becomes a linear function of omega. On the other hand, it should be proportional to omega to 2, square of omega in the presence of point node. So the density of state is seriously influenced by the nodal structure is pair potential. Okay, so then let's go to the second part. What is a Bogoliubov-Dujan equation? What is the tunneling effect understood in the standard BCS superconductor? Okay, so then let's look at metal superconductor junction system and how to understand the tunneling conductance in this system. As shown by Gieba, who got the Nobel Prize in 1973, in the presence of applied voltage, okay, the charge current start to flow. So because naively speaking, in superconductor, quasi-particle fills energy gap. So it is naively considered that quasi-particle cannot penetrate into this, how to say, gapped region. So then following this idea, the DI-dV becomes like that. IV relation becomes like that. And the DI-dV relation becomes like that. And density of state, it corresponds to density of states. So it has been wrongly believed that if we measure the DI-dV in normal metal superconductor junction, the resulting DI-dV expresses a line shape of density of states. But in this discussion, the very important concept is missing, so-called Andreev reflection. So Andreev reflection, which was predicted by Alexander Andreev in 1964, it's a very, very important concept in superconductor because all of the superconductor, including hosting non-homogeneity, injected electron should be reflected as a whole. So this process is generated due to the presence of condensation of Cooper pair in superconductor. So to correctly understand the charge transport problem of normal metal superconductor junction, we should take into account of the Andreev reflection process. For this purpose, so we must start from so-called Bogoliubov-Dujan equation. So let's assume the superconductor is a spin singlet S-wave case. In that case, if we write the Hamiltonian in the second quantization form, it is given like that by using field operator with spin index sigma. So then after some transformation, so because this field operator can be expanded like that or based on annihilation and creation operator, and finally we get that UN and Vn follow this so-called Bogoliubov-Dujan equation. This equation is similar to, in some sense, if Schrödinger equation, if we forget delta or delta star. And so UR and VR can be regarded as an electron part of quasi-particle wave function, and V is a whole part of quasi-particle wave function. So this is a famous guy, Bogoliubov and Dujan. So let's start to understand the property of this equation by looking at the very simple exercise. So where electron is injected from a normal metal based on one-dimensional model. Okay, the pair potential is assumed to be like that. In normal metal, it is 0, and the superconducting region, it is delta 0, constant. On the other hand, UX is 0, very simplified case. There's no barrier. So the material is uniform as far as we are considering normal state. Only the difference, whether there is a pair potential or not. So let's look at the wave function, possible wave function. In normal metal, basically, if we fix the energy, there are 4 kinds of wave solutions. And on the other hand, in superconducting region, also, if we fix this energy, so there are 4 solutions. Okay, so then let's go to next slide. So then let's consider normal metal superconductor junction system. So we consider an electron is injected from left side. This is wave solution 1, and group velocity is positive. On the other hand, Andreev reflected hole is here. The group velocity is negative. This is important. So this sign is positive, but group velocity is negative due to this dispersion. And normal reflection is here from solution 4, and it is given like this. This is a, how to say, wave function satisfying the boundary condition in normal method. On the other hand, in transmitted particle, there are two possibilities because transmitted particle group velocity should be positive. So 1' is an electron-like quasi-particle, and 3' is a hole-like quasi-particle. This is a transmitted quasi-particles. Okay, so then we postulate that wave function is continuous at x equals 0, and the derivative is also continuous at the x equals 0. But here we assume, it's a quite reasonable assumption that the magnitude of pair potential is much, much smaller than chemical potential or Fermi energy. And then omega, absolute value of omega or absolute value of energy is also much, much smaller than chemical potential. Then we can get the answer that process 3' and 4 can be negligible as far as we are doing this assumption. So then the obtained wave function is very compactly summarized, compactly written. So only the Andreev reflection occurs and it's a transmitted electron. So Andreev reflection and the process injecting the electron is reflected as a whole. So the probability is like that, and it's quite interesting. So in the energy gap, the Andreev reflection probability becomes unity. So all electron is returned back as a whole, as far as there is no barrier, namely the transparency in the normal state is unity. But it's a quite idealistic situation. In real material, such kind of things difficult to be realized because there should be a potential barrier or mismatch of Fermi surface inevitably exists. So then in general, the probability of Andreev reflection is smaller than unity. This is an important point. So then let's carefully consider taking into account of the normal reflection. Such exercises very simply can be done only assuming something like this potential Ux equal H delta X between normal metal and superconductor. Then we can automatically calculate the wave function, but the boundary condition is a little bit modified due to the presence of delta function model. So then, similar to the last analysis, so the pair potential, magnitude of pair potential is very much small. Then we can nicely return the coefficients A, B, and C, D compactly. And the final answer becomes like that. It is given by this quantity. Gamma is a ratio. It often appears in our analysis. It's a ratio to V0 to U0, and Z is a barrier parameter. Then Andreev reflection coefficient and normal reflection coefficient is compactly written like that. So this is a solution to understand that DIDV in normal metal superconductor junctions. And the line shape of the differential conductance is controlled by Z. Z includes the information of barrier potential. So the differential conductance is proportional to this quantity sigma s. It is expressed by 1 plus a square minus b square. And then finally, the differential conductance is given like that. It can be written quite compactly, analytically like that, inner gap and outer gap like that. And so let's plot the conductance spectra for Z equals 0. So within the energy gap, the normalized value of conductance by its value in normal state becomes like that, and it becomes constant to in the energy gap, within the energy gap. On the other hand, with the increase of magnitude of Z, so the line shape of conductance approaches to that of density of states. So this is a standard wisdom. So in tunneling spectroscopy. Okay, so let's, in the case of two-dimensional case, it is straightforward to extend this idea, or the momentum parallel to the interface is conserved. And if we fix momentum ky, it is possible to reduce the problem to simple one-dimensional system. Okay, so then let's go to the explanation about so-called Andreev bound state. So the Andreev bound state has been known since 1963. So Dujan and St. James has done very important seminal works. And after that, Macmillan, Thomas, and Royal contributed so much to understand this very important phenomenon. So if we consider normal matter attached to superconductor, the energy levels of Andreev bound state is generated in the energy gap, within this energy gap region because it's a metallic. But the energy level is given by this quantized value when epsilon n is much, much smaller than delta. So how to understand this Andreev bound state? It's a good exercise. So I'd like to show from now. So let's consider one-dimensional model. The key point is that in normal metal region, wave function should disappear at x equal minus L, it's attached to vacuum. So wave function can be written like that. Electron part and hole part can be written like that. On the other hand, in superconductor region, we must postulate the condition that wave function never diverges when we take the limit x is infinite. So the imaginary part of k plus is positive and the imaginary part of k minus is negative. So this combination, the unique combination which satisfies the boundary condition. So then this means that in normal region, we must take into account of all possible solutions to make a boundary condition at x equal minus L. So then, so this is a boundary we postulate a boundary condition at x equals 0, and we can use these conditions because the Fermi energy is much, much larger than pair potential delta or energy we are now looking at. So finally, we get a very compact relation, so-called bound state conditions. And after some simple manipulation, the energy level of bound state E equal epsilon n should satisfy this relation. It's a nonlinear equation, a little bit complicated. But if we assume that epsilon n is much, much smaller than delta 0, the energy level is nicely written like that. So this is a story how to understand Andreev bound state. Okay, so to Dujan St. James time. So then let's go to the main part of my lecture. So tunneling effect in unconventional superconductors. So what should be modified? So then in unconventional superconductor, as far as we know, so let's imagine that superconductor with nodal structure, line node structure realized in high-TC cuprate, the density of state has a such like V-shaped behavior where the density of state is proportional to energy. So naively speaking, so we imagine that from the analogy to tunneling spectroscopy in S-wave superconductor, the resulting tunneling conductance might be there like that. But story is not so simple. So because in unconventional superconductor, pair potential changes sign on the Fermi surface, and then quasi-particle, Bogoliubov particle, feels different sign phase of pair potential depending on the directions of motions. This is an important point. So for this purpose, okay, let's go to this equation, Bogoliubov-Dujan equation. Strictly speaking, so Bogoliubov-Dujan equation becomes a little bit complicated because Cooper pair is formed between two electrons at different places. So this is a quite rigorous formula taking into account of anisotropy. And also we should take into account of spin degrees of freedom. But if we consider, for example, spin singlet case, and there is no magnetic potential or spin orbit coupling in normal state, then this 4x4 Hamiltonian can be decomposed into two blocks of 2x2 matrix like that. So then the problem becomes a little bit simplified. So the problem is how to treat this delta RR prime, which is a non-local quantity. It's a little bit complicated stuff. So similar to spin singlet case, spin triplet superconductor with SZ equals 0, we can do similar analysis. And after decomposition into 2x2 matrix, the resulting Bogoliubov-Dujan equation is like this. It's an extended version from a well-known S-wave Bogoliubov-Dujan equations. So to treat this problem, so this is an equation and 2x2 equation. And so to treat this problem, we should use some kind of approximation to treat it analytically. Of course, numerical calculation in tight binding model is available now, but to understand the good physical picture, some kind of analytical analysis is quite useful. So the most important assumption is that the Cooper pair is formed by two electrons on the Fermi surface, and also the effective pair potential is determined by, please wait a moment, the pair potential is determined by the direction of the motion of electrons. Okay, so then, please wait a moment. Okay, so then let's look at the wave function again. So wave function, how about the wave function? The spatial dependence of wave function is decomposed into two parts. Of course, wave function is on the Fermi surface. It should have an oscillatory part. And also, we multiply. There's a slowly varying envelope function. So the wave function can be decomposed like that. And we call psi this one as an envelope function. And spatial change is very slow as compared to the inverse of Fermi momentum. So how to treat it? So then if we assume such kind of, if we do such kind of decomposition and assume that the pair potential can be expanded like that, and here X is a relative coordinate of R and R prime, and R, large R is the center of mass. So then it can coordinate, center of mass coordinate. So then pair potential, it's a straightforward transformation. And so then we transform like that and applying this approximation. And we introduce a fully transformed form of pair potential as a function of relative coordinate. So then we get to this answer. So finally, the envelope function satisfies this relation. What does it mean? So the envelope function feels pair potential on the Fermi surface, and the pair potential, the important information is that which direction quasi-particle goes. So only the direction of quasi-particle determines the pair potential at each position. This is an important message. So it becomes very useful to treat this rather complicated equation. So then let's, apply this idea for normal metal superconductor, unconventional superconductor junction originally done by Christopher Bruder. So the insulator model, insulator is modeled by delta function potential, and we assume flat interface. So then let's do this calculation. And in that case, theta, injection angle is a good parameter to, decompose, to write down wave function like that. In superconductor region, wave function is characterized by theta. And so it decomposed into plus exponential IKF cos theta term and exponential minus IKF cosine theta term. And this is an envelope function. And this envelope function is written analytically. I do not mention so much time. So, but it can be given like that. And here A is Andreev reflection coefficient, and B is normal reflection coefficient. And this function omega is a very important quantity. We take that the imaginary part of this omega is always positive to be consistent with causality. So then we postulate the boundary condition. To discuss the boundary condition, we should apply this boundary condition of total wave function, including oscillatory term. And then we get Andreev reflection and normal reflection coefficient analytically like that. And here is a pair potential. This function gamma is quite useful. Gamma is given by pair potential delta and also energy, since omega plus is given by these combination, by these functions. And also gamma minus is given like that. The important difference between conventional spin singlet S-wave cases is as follows. In S-wave singlet case, gamma plus equal gamma minus is satisfied, always satisfied. On the other hand, in D-wave or P-wave or chiral P-wave or unconventional case, gamma plus and gamma minus becomes a basically different quantity each other. This is a very important point. And then finally, we get the compact conductance formula. So it is given like that. In this formula, the key parameter is sigma n. Sigma is the transparency of the junction in normal state, and also energy and pair potential, effective pair potential felt by quasi-particle on the Fermi surface. So then let's look at this equation more in detail. So what this equation tells us. So then one of the important messages is that the denominator of this equation tells us the condition of the surface under F bound state. So it's a surface under F bound state, it's an inner gap state localized near the surface. So if we take sigma n almost zero, sigma n approaches zero, and postulates a condition that requires a condition that denominator should vanish. So it is reduced to be 1 equal gamma plus times gamma minus. So this is a, how to say, so-called surface under F bound state conditions. Okay, so then let's apply it to well-known cases, D-wave case or P-wave case. So first look at D-wave case. In that case, pair potential is given like that. Why it is relevant to high TC cuplet, I would like to mention more in detail later. So, but naively we consider such kind of pair potential, then delta plus equal delta minus equal delta 0 sine 2 theta, because delta minus is a potential with pi minus theta, and delta plus is a potential for theta. So then it is given like that. And apply these pair potential into this equation, we get this answer, and automatically we can see that E equals 0 is a solution, which is firstly mentioned by Chiar and Fu. On the other hand, PX wave case, it's a standard model discussed in superfluid helium-3, and we can choose delta plus equal minus delta minus equal delta 0 cosine theta. In that case, we can also get the answer E equals 0. So the conductance formula includes a very important information about surface bound states, surface under F bound states. So very recently, we discussed more general situation. So by analyzing 1 equal gamma plus gamma minus, and postulate assumes that the magnitude of delta plus and delta minus are equivalent to each other, it includes many cases, including chiral P wave or something like that. Then the bound state solution can be given like this, and delta phi equal phi minus phi plus, and this exponential I phi and exponential minus I phi is given like that. Then, after some calculation, we get the interesting formula like that. The conductance, if this condition is satisfied, the charge conductance here, the sigma r, sigma s is a sigma n times sigma r, important point, important factor in the numerator. It is given by this completely analytically, and gamma is given by the, how to say, function of transparency in the normal state, and EB is a position of under F bound state. And it includes a very important message that if we fix the energy E equal EB, sigma S E theta is always 2, perfect resonance occurs. So just at the boundary, under F bound state level, so sigma S E theta becomes 2. So this is published in Journal of Superconductivity and Non-Bell Magnetism. It's a how to say congratulation issue for the 80th birthday of Brian Josephson. Okay, so then let's look at very interesting situation where delta plus equal minus delta minus is satisfied. It's a most dramatic, interesting situation. In that case, this sigma s becomes sigma s as sigma n times sigma r. This sigma s is simply written like that. So it's a, how to say, it means a conductance has a resonant structure at E equal, EV equal 0. So, and the width of this resonance is given like that quantity. So this means that zero bias conductance peak becomes sharper and sharper with a decrease of transparency. On the other hand, at EV equal 0, so the conductance sigma s is always 2 independent of transmissivity in the normal state at the interface. So I would like to mention the obtained result is essentially the same as in the case of tunneling via Majorana fermion. Majorana fermion is now studied in many topological superconducting systems, but I would like to say that our obtained formula more than 20 years before can expand easily in the tunneling problem, including Majorana fermion. So then let's go to the relation to how to say high TC cupulate. So crystal structure of high TC cupulate is given here. So here is a, how to say high TC crystal structure, and also this is a bismuth strontium calcium kappa, and it is a yttrium barium kappa. But the important message is that how to say kappa to plane plays an important role. So this is an important point. And so then this is a lattice structure. And if we consider in that, the relevance to high TC cupulate is as follows. In high TC cupulate, Cooper pairs formed between some kind of lattice model and adjacent to, how to say, Cooper pairs formed between two adjacent lattice sites. So if surfaces along this direction, then in the continuum model, we have used delta plus and delta minus is given like that. On the other hand, for 110 surface model, delta plus and delta minus is given like that. Delta plus equal minus delta minus equal delta 0 sine 2 theta. So this is a relation to high TC cupulate. And if we cut in the intermediate angle, so then it can be given like that. So then the image of this picture is like that. Here's the angle alpha, and this is a crystal axis of kappa or directions. And we cut the surface, and then we inject electron from normal metal was a tip of scanning tunneling microscopy. And so the Andreev bound state is generated near the interface or surface of D-wave superconductor. This is a rough image. So then let's apply a formula for various orientation of angle, alpha. So alpha equals 0, as seen from here. So with the increase of the barrier potential, the conductance changes like that. Quite similar to spin singlet to S-wave superconductor, because the inner gap conductance is suppressed with the increase of Z. So in this case, there's no surface Andreev bound state. Why there is no surface Andreev bound state? Because there is no sign change on the pair potential felt by a reflection process. And I would like to later explain that this absence of zero bias conductance peak is due to some kind of accidental topological cancellation. Okay, so then let's go to alpha equal pi over 8. In that case, with the increase of Z, the magnitude of tunneling conductance around zero voltage is hugely enhanced because due to the presence of zero energy conductance peak. And so the future, for example, C, curve C is very different from local density of states in bulk. So there's a big difference between curve C and curve D. Okay, so then let's look at alpha equal pi over 4. This is an extreme case because all of the quasi-particle fields, injected quasi-particle fields, zero energy state, independent of the injection angle. So with the increase of Z, so the resulting charge conductance becomes like that. Okay, it's quite different. From line shape, it's quite different from local density of states in bulk. Okay, so then let's look at the, how to say, experimental situation. So scanning tunneling spectroscopy has been done by my collaborator, Professor Kashiwaya, when he was working in Tsukuba, some National Institute of Tsukuba more than 20 years before. At that time, there's a good postdoc from Germany. The name is Lambert Alf, and he has done very important contribution about this topic. So then he measured, Kashiwaya measured tunneling spectroscopy on the surface of YBCO, well-characterized surface, and it is produced on the strontium titanide oxide surface, and then nicely zero bias conductance peak was observed. On the other hand, for 100 direction, there is no zero bias conductance peak to be consistent with our theory. And also, sorry, please wait a moment. Okay, Professor Iguchi in Tokyo Institute of Technology, that's done. Okay, did YBCO silver junction system and measured tunneling conductance. So 110 oriented direction, they measured, actually they observed zero bias conductance peak. On the other hand, it is absent in 100 direction. So here we briefly mention about our formula is how to say quite general. If we consider such situation, because at that time, Professor Matsumoto now in Shizuoka and Professor famous guy Shiba predicted that D plus I pairing is generated near the surface. So then in that case, tunneling spectroscopy should have a splitting, but our formula can be taken into account of such kind of spatial change. In that case, gamma plus and gamma minus follows this type of Ricketts equation. So I would like to say that our formula is quite general. Even in the presence of spatial dependence pair potential, we can apply Tanaka and Kashiwai's formula in that rather complicated system. Okay, so after 2000, Kashiwai-san has measured tunneling conductance or LSMO YBCO junction system. It's quite an interesting experiment. To interpret this result, it's a little bit complicated because LSMO is a strictly speaking ferromagnet. And with the increase of magnetic field, zero bias conductance peak survives. So it cannot be understood within a spin singlet pairing, I think. So to understand this correctly, we must take into account of the triplet component, so-called odd frequency spin triplet component. This is very interesting stuff will be discussed today by Dr. Suzuki later, I think. Okay, so then I'm very much encouraged. Very recently, such kind of activity is still continuing. Alex Hyatt in Technion in Haifa in Israel, they measured very interesting zero bias conductance peak between high TC Q-plate and semiconductor gallium nitride. So they measured very heavily doped gallium nitride and obtained the zero bias conductance peak like that. So this is a current experiment published in Journal of Physics Condensed Matter very recently. So then I'd like to mention the physical meaning or importance of surface Andreev bound state to connect latter part of the lecture. So Andreev bound state is originated from the sign change of pair potential, where electron, hole, and hole is reflected as different trajectory. At that time, delta plus and delta minus are different sign each other. Then, if we fix the momentum parallel to the surface, then the energy spectrum becomes like that, and green line and yellow region means how to say continuum level, and between continuum level, so the surface Andreev bound state exists just at equal 0 as far as time reversal symmetry is not broken. So then later I would like to mention that this flat dispersion is obtained from the topological nature, including this included in the Hamiltonian. So I would like to mention that in this lecture, so first part of this lecture, I first mention that Andreev bound state is a quite well-known stuff from very old times. So, but normal metal spin singlet SF superconductor junction system, the position of Andreev bound state is quite sensitive to, for example, length or in transparency, various things. And so such kind of Andreev bound state is not called topological origin, topological Andreev bound state. And so it depends on various boundary conditions. On the other hand, the present D wave or P wave surface Andreev bound state is topological because it does not depend so much about the spatial change of pair potential as far as Hamiltonian has a, how to say, symmetry. So then it's a very different Andreev bound state. So I'd like to explain in the latter part of my lecture why it is topological. So then, in this lecture, I do not mention about in detail about chiral P wave or P wave case. I briefly mention in the finally. So chiral P wave case, the boundary condition, surface Andreev bound state condition is given like that, and theta is a, how to say, injection angle. So then the resulting bound state, resulting energy dispersion of Andreev bound state is given like that. It is proportional to sine theta, and it means that it is proportional to momentum ky parallel to the surface. On the other hand, px wave, I already mentioned that it has a flat band zero energy state, flat band dispersion. And then if we calculate similar to spin singlet case, very easily it can be done. For px wave case, it's a sharp zero bias conductance peak. Py wave case, like a dx square minus y square. There's no zero energy peak because all quasi particle feels no sign change of pair potential as a reflection process. On the other hand, chiral P wave case is a little bit complicated because the energy level of Andreev bound state depends on momentum ky. So then after summing up all contribution, of course it depends on the model of transparency in the normal state. But if we use something like standard data function model, so it has a dome-like structure. So there's a clear differences between these two, between these three. So then I'd like to mention about some review article we have published more than 20 years before reports on progress of physics with Kashibaya-san and relevant papers or review articles. Nice review by Professor Eschrich and also Professor Golubov. It's a quite nice review of Josephson junction and Professor Rofanda, Shumeiko, and Wendy, similar to our reviews. Okay, so I finally mentioned about the recent developments about this topic. Recently, some kind of extension has been done by Dr. Tamura. He introduced more general conductance formula available for not 2x2, but 4x4 Bogoliubov-Dujan equations. In that case, the difference is that gamma minus or gamma plus is no more scalar, but it becomes a 2x2 matrix. And however, in that case, if normal metal does not include different, does not include magnetic moment or spin orbit coupling, it can be done, it can be written straightforwardly. The sigma s bar is given like that. It's a trace of 2x2 matrix. It can be compactly written. So thanks to this formula, so it becomes quite easily to calculate, for example, B phase of spin triplet pairing. So it's a three-dimensional model, and it is possible to calculate very easy. So we can get that the bound state, Andreev bound state energy level is determined by delta zero sine theta. It's a cone-like structure in, how to say, two-dimensional surface. And the dispersive surface Andreev bound state cone type, after summing up all contribution, does not have a zero bias conductance peak. Although it has a zero energy state at theta equals 0, but it's only a point in the surface Brillouin zone, and the contribution is quite small. So then zero energy peak, zero bias conductance peak never appears. So it was firstly mentioned by Asano-san, but recently such kind of strong formula appears and we can get this answer very easily. So thank you very much. I will finish the first lecture. So if there is some question or comments, please ask me.
Hello, thank you very much. So maybe you want to ask a question? I think Professor Okenchuk.
So is it okay? They hear me? So Igor Lukianchuk, the question is as follows. Actually,
okay. Please speak more loudly.
Of 80s, it's classical work of Gorkov and Volovitz. They show that if you take into account the crystal symmetry group and spin orbital coupling, the classification of P, D, and so on pairing will be changed according to very special symmetry group. And in particular, you will have no anymore the lines of zeros. I think only points which are topologically protected. How this change of classification and disappearance of zeros at the line will be critical for your case.
Could you please repeat again? You mentioned that in the presence of spin orbit coupling, shape of pair potential changes. Well, what do you want to say? I'm sorry, I cannot hear your voice well. Can you hear? I'm sorry,
Do you hear the question?
Can you hear my voice? Sasha, can I hear my voice?
Hear you. One moment. No, I think everything should work.
Yes, can you hear?
First, Anna, can you speak? We don't hear you.
Yes, I can hear your voice.
The microphone possibly is muted.
No, he can.
Yeah, but
I'm sorry, could you please repeat your question again?
okay. So, do you hear me?
Yes, now it's okay. Last
Okay,
time
fine.
it is quite
So
difficult.
I wanted just to tell that in the middle of 80s,
In the middle of 80s, okay.
Gorkov shown that if you consider the real crystal symmetry group of the superconductor, also coupled with spin orbital coupling, the symmetry classification will be quite different from this PED and so on pairing. And in particular, result of this change of the symmetry classification will be that the lines of zero, which is the case for D-wave parent, will disappear. And you can have only the points of zeros, but points will have the very, very particular topological properties. I mean, you can have different phase fit and so on. How this change of the group classification, which is more realistic for the crystal, will affect your results?
Okay. Maybe you are mentioning about Brandt's theory. Is it relevant to Brandt's theory?
Sorry. No, I did not hear.
Brandt's theory. So I understand what you want to say. So in triplet case, whether the node is stable or not must be checked quite carefully. Yes, I agree. So actually, I have studied such kind of problem with Dr. Kobayashi before. And on the other hand, spin singlet case, I think spin orbit coupling does not influence so much on the line shape of conductors. So whether PX wave pairing is really stable or not, it's a good question. So in actual three-dimensional material, I'm not sure it is really stable or not. But in the presence of some symmetry, for example, spin rotation symmetry or something like that, it can be possible. But the work of spin triplet P-wave pairing can help to understand the charge transport in the presence of Majorana fermion now. On the other hand, D-wave case, I think spin orbit coupling does not make so much influence. So it's a good point. And actually, we have studied charge transport behavior in the presence or absence of spin orbit coupling for D-wave and P-wave case. In D-wave case, actually tunneling spectroscopy is not influenced in the presence of spin orbit coupling. On the other hand, in triplet case, it is actually influenced. And maybe it's relevant to your, comment. And whether line node or point node is stable or not has been discussed from all time before Ueda and Sigrist's review article.
Okay, thank you very much.
Thank you.
Okay.
So let's make a break now, 10 minutes. Yeah? And 10 minutes. We'll continue
6
o'clock. 10 minutes at 11 o'clock our time.
Okay, 11 o'clock. Okay.
In 10 minutes. The recording started. Okay, please.
Okay, thank you very much. So the latter part of my talk, I first start from topological invariant and surface Android bound state. So what is a topological invariant? So then first start the, okay. So then, first start this part. So what is topology? Topology is kind of concept, a classification of the properties of space that are preserved under continuous deformations, stretching and bending, but not tearing or gluing. So then, as seen from this picture, so mag cup is equivalent to donuts. On the other hand, ball is a different shape. So it can be distinguished between these two. So how this concept appears in condensed matter physics. So Yada-san has made a very nice explanation using very simplified 2 times 2 Hamiltonian. Okay, 2 times 2 Hamiltonian. So Hamiltonian can be written like that, ax, kx, sigma x plus ay, sigma y. Sigma x and sigma y is how to say power matrices like that. And automatically it can be diagonalized very easily, and the eigenvalue becomes like that. And here we assume that ax and ay are real numbers to be consistent with hermiticity, and x and ay cannot be zero simultaneously, so it should be a gapped model, and the Hamiltonian matrices at kx equal minus pi or pi are the same, and the parametric plot of the Hamiltonian draw a circle like that. So then ax and ay is, if we choose ax and ay like that, it becomes like that. So it's actually parametric circle. So then let's consider how to say two situations. Here ax is chosen like that. This circle draws like that. On the other hand, if we choose x and ay is like that, circle is located here. So there's a question, and are there continuous deformations without gap closing? So the answer is no. So it is impossible to connect, to change from here to here without gap closing. So then let's look at this situation in a different way. So in this case, left situation can be regarded as that. So how to say this circle surround this z equals 0 like that. On the other hand, this circle is located like that. This means that z-axis, for example. So it's different each other. So we can distinguish between these two as a topologically different phases. So this is a very simple explanation how to understand the topology in condensed matter physics. So topological phase is characterized by topological invariance. In the present case, winding number is a topological invariant. So then let's look at, return back to the problem of the D-wave superconductor, for example. So in D-wave superconductor, so it's a good question why zero energy surface and bound states appears. Of course, we can understand the origin by solving Bogoliubov-Dujan equation and looking at the conductance formula of bound state problem. But as a way to understand, there's a solution based on topology. So first, it should be mentioned that topological invariant defined momentum space is possible, and the origin of node in unconventional superconductor can be understood recently by so-called topological number. So I'd like to mention in relevance to D-wave superconductor case we have been studying. So this work was mainly done by Professor Sato. He's now working with Yukawa Institute in Kyoto University. So then let's start from 2 by 2 matrix written in momentum space. So momentum space, it is given by like that. Hamiltonian is given by Gz, delta minus Gz, and delta is chosen like that for spin singlet case, and we choose Z equals 0 pairing. So then we can write down dz equal minus dz like that. And winding number can be written like that. And Gz is a kinetic energy in normal state, and delta is a pair potential written in momentum space. And we integrate theta. For example, if we write it in some kind of periodic system from minus pi to pi, and infinite system, continuous system, we can write it minus infinite to plus infinite by introducing some regularization. So then, after some manipulation, winding number can be transformed like that. So we sum up momentum kx where Gzk equals 0. This means only on the Fermi surface. And we count two integers like that, signature of delta k. It can be plus 1 or minus 1. And also this is a signature of velocity. It can also become 1 or minus 1. So then counting these products on the Fermi surface, we can obtain winding number. So it's a topological invariant is defined for effective one-dimensional Hamiltonian for fixed Ky. So let's look at the single Fermi surface case. In that case, Fermi surface is like that, and this equation can be transformed like that. So the non-zero winding number means that sign of pair potential here and here, the point P and P prime are different each other. So delta times delta is negative. So this is a known condition. Actually, we have proven in this by solving a Bogoliubov-Dujan equation, the quasi-classical approximation before. So then let's look at the physical meaning of winding number. If we integrate me as a nodal point, it is possible to define winding number. So let's look at this D-wave superconductor. If we count the winding number at this red point, red nodal point and yellow nodal point, it becomes -1 and -1, and also +1 and +1. How it becomes like that? So then let's start from the understanding of winding number around point A. So here, cosine theta is given like that quantity, and sine theta is like that. The sign of delta K is positive in first zone and third zone, and negative in this region and that region. On the other hand, this blue region, it's inner Fermi surface, so Gzai is negative. Okay, so then by looking around A and starting from the point from here, so then first cosine theta is positive because it is Gzai is positive, and sine theta is negative. But if we go to this region, cosine theta becomes negative. And yes, please look here, cosine theta is negative, and sine theta is negative. And then let's go to this region. Cosine theta is negative, but sine theta becomes positive. And here, both of these quantities becomes positive. So if we look at how to say, plane of cosine theta and sine theta, it's a clockwise. So it can be regarded, winding number is minus unity. On the other hand, around nodal point B, let's start from here. Cosine theta is negative because it is inner Fermi surface. And also, sine theta is plus. On the other hand, here is negative and both negative, like here, and here is plus and minus in this region. And in this region, both of these quantities positive. So it's anti-clockwise, okay. So then, following this idea, we can understand the sign of, we can understand the value of winding number at each nodal point. And then winding number for various trajectories can be counted like that. And please look at, for example, contrast C1 and C3. There's a -1 difference because here is a nodal singular point. And also winding number jumps from C3 to C4 because there are two nodal points here. Each of these nodal points has topological number, singular point, and it changes from -1 plus 2 equal 1 because both of these nodal points have a topological charge +1 and +1. So then zero energy state, surface and Drake bound state appears only when winding number is non-zero. So it can be expressed like that. In this moment of, in this KY region, there is no Fermi surface, winding number is 0. On the other hand, here is -1, and here is +1, and here is 0. Okay, so this is a, how to say, understanding of winding number for fixed KY. So let's apply this idea for that, okay, before that, we must look at another important concept. So from the bulk edge correspondence, there exists a gapless states on the edge only when integer W1D is non-zero. And on the other hand, there's a very important symmetry originating from Bogoliubov-Dujan Hamiltonian. So in this BDG Hamiltonian, some operator exists which anti-commute with original Hamiltonian. It is so-called chiral symmetry. If such kind of operator exists, so zero energy Andreev bound state is also eigenstate of chiral operator, which anti-commutes with Hamiltonian. In this Hamiltonian, this chiral operator becomes sigma y. And N0 plus is a number of zero energy state where the eigenvalue of sigma y is unity, and N0 minus is a number of zero energy state where the eigenvalue of sigma y is minus unity. And it's a so-called index theorem. So winding number W1D becomes N0 plus minus N0 minus. So actually, if we solve the zero energy state solution of D-wave superconductor, it can be automatically written like that. And the important point is that we must discuss how to say pair potential, which is available for all over the momentum k. So we define a little bit artificially, delta k is like that. Then zero energy surface Andreev bound state solution is automatically given like that. And depending on the signature, depending on the sign of ky, this sign changes, but it can be written like that. Then we have checked that this theorem is satisfied. So for example, if superconductor is located or positive x and the surface is here, so N0 plus and N0 minus takes these values for ky is positive and ky is negative, and then this relation, we can check that this relation is satisfied. On the other hand, superconductor is located to left side, so additional sign appears, but we can check that this relation is satisfied. This sign difference can be understood easily by introducing odd frequency pairing generated at this region, but this topic will be discussed by Suzuki-san later. Okay, so let's return back to the problem of tunneling spectroscopy. So if alpha equals non-zero, then we should expect zero bias conductance peak. Is it possible to understand the generation of zero bias conductance peak in the language of topology? It's okay. So let's discuss. So if alpha is non-zero, so let's calculate winding number like that. If momentum ky is located here, winding number is zero. On the other hand, winding number becomes minus unity, and here winding number is zero, and here winding number is unity. So as seen from here, there is some momentum region, or there is some injection angle region where winding number becomes non-zero. At that region, we can expect the existence of zero energy state, surface zero energy state, and the resulting charge conductance should have a zero bias conductance peak. Okay, so this is a case. On the other hand, for alpha equals zero, actually there are topological interesting stuff here, but there is a cancellation. So plus one minus one equals zero. It's a very simple mathematics. So then winding number here is zero, although if we change the contour from here to here, and we met these two singular points, but 1 minus 1 equals 0. Then winding number is always 0. So then there's no zero bias conductance peak. This is a new interpretation which is available to understand the absence of zero bias conductance peak in this configuration. Okay, so it can be regarded, and zero energy surface Andreev bound state vanishes due to the topological cancellation. Okay, so let's look at the P-wave case, quite similar to follow D-wave case. In that case, wave function of zero energy state can be written like that. But the big difference is here, there is no signature ky. So the absence of signature ky seriously influences on the symmetry of hidden odd frequency pairing, and also charge transport behavior if we consider diffusive normal metal attached to superconductor. And in P-wave case, we can actually check that this index theorem is actually satisfied when superconductor is located for positive x and it is located for negative x. So it's okay that such kind of relation is satisfied. So then we would like to summarize. So if superconductor is located to x is positive, we can satisfy index theorem like that, both for D-wave case and P-wave case. But there are big differences between two. In D-wave case, winding number changes sign for positive ky and negative ky. Okay, positive and negative. On the other hand, px wave case, there is no sign change. So is it possible to detect such kind of sign change in charge transport behavior? So it's actually possible. So we'd like to explain later. So first we'd like to summarize up to now. So zero energy Sachs and F-bound state can be understood by the topological invariant defined in the bulk Hamiltonian, and zero energy Sachs and F-bound state can be classified by the chiral operator, which anti-commutes with original Hamiltonian, and we can show that index theorem is actually satisfied in the surface state problem of D-wave superconductor. So the image is like that. So here is how to say zero energy state, but the nature of zero energy state of P wave and D wave is different. In P wave case, the sign of winding number is always always negative, for example. Of course, it depends on the choice of gauge, but there is no sign change. On the other hand, D wave case, sign change occurs, or whether it is positive ky or negative ky or positive ky. So the problem is that this difference, so it's an odd function and it's an even function, is it possible to detect its difference? So it can be possible if we consider diffusive normal matter attached to superconductor. So actually, I have collaborated with Professor Golubov 13 years before. That the charge transport behavior in diffusive normal matter is very much different when the dominant Cooper pair is even frequency spin singlet S wave or odd frequency spin triplet S wave. So this so-called anomalous proximity effect is only possible for how to say spin triplet pairing. So I'd like to mention from now. So then we have clarified before a topological study, I have clarified the existence of quite unusual proximity effect rather earlier time, more than 60 years before with Professor Kashiwara. We have calculated Usadel equation following the boundary condition, extending the boundary condition originally introduced by Yuri Nazarov, and get the answer that there is a big difference between spin triplet case and spin singlet D-wave case. In spin singlet D-wave case, proximity effect is unfortunately absent in diffusive normal matter. On the other hand, in P-wave case, very dramatic proximity effect, we have clarified that the local density of state has a zero energy sharp peak. In usual case, the density of state in diffusive normal matter, if we consider spin singlet S-wave superconductor, it should have a zero energy deep-like structure at zero energy. Actually, Professor Golubov and Kupriyanov derived this relation in 1988, and in usual case, it's a gap-like structure. But here, in P-wave case, there's such kind of sharp zero bias conductance peak appears, zero energy peak appears. So is it relevant to topology or not? I would like to mention from now. So if we consider, for example, zero voltage resistance, very interesting thing occurs. Actually, I have clarified. At that time, I do not know Majorana fermion at all and do not know topology at all, but calculating Usadel equation straightforwardly, we have obtained that if we consider px wave superconductor junction, very dramatic thing occurs. Here is RD is a diffusive resistance in diffusive normal matter in normal state, and RB is a resistance at the interface. So with the increase of RD, in usual case, it is shown by Karl Benecke and Anatoly Volkov that the reentrant behavior of total resistance appears due to the presence of retroreflectivity of Andreev reflection. So on the other hand, case B and C, in that case, proximity effect is absent. So the total resistance is a linear function of RD. On the other hand, case D is very, very unusual because total resistance is independent of RD. This means that charge conductance in this junction is completely quantized. So this problem is actually very interesting. And Professor Asano-san and also Ikegaya-san now in Stuttgart and also Suzuki-san in Nagoya are very much interested in this topic. So they want to clarify the physical origin more in detail. So they have started to look at the numerical calculation beyond quasi-classical approximation. they start to fix, for example, number of total channel by considering finite thickness of wire and focus on zero voltage conductance, very limiting case where Rn is a resistance in diffusive normal metal becomes infinite. In that case, naively speaking, GNS is a charge conductance, becomes zero. This is a usual standard case because Rn here is infinite. On the other hand, in spin triplet case, it can be quantized and it is proportional to some special integer appears. What this integer? So it's relevant to Atiyah-Singer's index, but we would like to mention here. So then Suzuki-san and Ikehara-san has done numerical calculation. And so they plot the function of Gn of total conductance like that. They fix the total number of channels equal 9, and n plus minus is the number of channels, number of zero energy state, which is characterized by winding number. So n plus is the number of channel where winding one-dimensional winding number is unity, and n minus is minus unity. And n0 is the number of normal channels, because in dx wave case, due to numerical reason, so the perpendicular injection does not feel pair potential at all. So it is called normal channels. So then in px wave case, n plus equal 9, n minus 0, and the integer n0 energy state can be counted 9. So it becomes actually like that. And also F wave case, like that. And dxy wave case, it is complete cancellation occurs because n plus and n minus are the equal number. And n0 energy state is subtracted each other, it becomes 0. So it's quite interesting that a quantization of conductance appears only for spin triplet superconductor. Because in spin singlet superconductor case, maybe, spin singlet superconductor case, as seen from the, please wait a moment, as seen from here, yes. So spin singlet case, the positive region and the negative region are equivalent to each other. So they cancel each other. So totally, the number of channels, n plus minus n minus, is 0. So then charge conductance, yes, charge conductance here becomes 0. So this is a very important message. And so the index theorem actually appears in the charge transport problem. So the minimum conductance of the junction becomes quantized, and the n0 energy state is a number of perfect transmission channels, and the n0 energy state is given by n plus minus n minus, and it is relevant to Atiyah-Singer's index. So the, how to say, winding number to understand charge transport behavior from the viewpoint of topology is very, very interesting and very important. So then let's look at, yes, n0 energy state is given like this quantity. Okay, so before closing this section, so I would like to mention as a type of Andreev bound state, so-called Andreev bound state, which has a dispersion. So it is known from the study of ruthenium oxide or helium-3 or many exotic superconductor. If the chiral P-wave superconductor is realized, then the Andreev bound state has such kind of dispersion. On the other hand, in chiral D-wave case, it becomes like that. And in that case, contribution from zero energy is not so much. As far as we are considering standard tunneling problem, zero bias conductance peak is not so much enhanced. And the helical P wave like that, the resulting charge conductance is quite similar to chiral P wave. Okay, so this is a summary of the understanding. What is Andreev bound state and what is topological Andreev bound state? There are so many Andreev bound states all over the world in the superconducting society, and Andreev bound state is a very universal concept which inevitably exists in homogeneous superconductor. And so there are so many non-zero energy Andreev bound states. But Andreev bound state, which is how to say, protected by bulk edge correspondence, it can be called topological edge state. And there are several types of Andreev bound state without dispersion or with dispersion. Okay, so then let's go to the problem of Majorana fermion, because today the concept of Majorana fermion is widely spread and many people are interested in Majorana fermion. What is Majorana fermion? So my message is very simple. Majorana fermion is a special type of zero energy surface Andreev bound state. So is it relevant to D-wave zero energy state or not? Actually, it is a little bit relevant. So D-wave case, the zero energy state solution is given like that. But we must be careful that this constant C, it depends on the direction of spin and also sign of momentum Ky. Ky is the momentum parallel to the surface. So it's a little bit complicated. But if we choose C carefully, then we define this type of Bogoliubov operator. Bogoliubov operator satisfies such kind of relation. So annihilation, and there is actually relation between annihilation and creation. But we must be careful that the spin of annihilation operator and creation operator are different to each other. On the other hand, in P-wave superconductor case, if we, P-wave superconductor case, as far as we are considering opposite spin pairing, so Cooper pair with Sz equals 0 or D vector is along Z direction, then this Bogoliubov relation is similar to D wave 1. On the other hand, okay, so if we consider spin triplet P wave superconductor with equal spin pairing, the situation becomes different. So this is how to say Cooper pair with opposite spin pairing satisfies for both spin singlet and triplet. On the other hand, if we consider equal spin triplet pairing, this relation is satisfied. So if the Hamiltonian can be decomposed in up and down spin sectors, so this zero energy state can be regarded as a Kramer's pair of Majorana fermions, a little bit complicated Majorana fermions. It has a spin degrees of freedom. On the other hand, most dramatic and most interesting case is realized for spin fully polarized case. And in that case, spinless fermion is generated. So because only the one spin sector exists. In that case, gamma k equal gamma minus k dagger is satisfied. It is called Majorana fermion, originally introduced by Majorana in 1933. Okay, so are there any good example where Majorana fermion is realized? So recently, there is a quite well-known model, so-called Kitaev model. It's very much familiar in condensed matter society. This model is very simple, but the merit of this model is that we can study topological, non-topological transition by simply tuning the parameter. Actually, it's a lattice model. So it's a hopping time and chemical potential and pair potential. Pair potential is very simply given like that. And then the structure is very simple. We can get the quasi-particle spectrum very simply like that. In this model, there are two phases. Actually, how to distinguish between two phases as follows. So this spectrum can become 0 at k equals 0 and mu equal, for example, plus minus t. In that case, so if the energy gap closes and by crossing the crossing point, we can change from one phase to another phase. So if chemical potential, magnitude of chemical potential is larger than hopping integral, transfer integral, so non-topological phase is realized. In that phase, there is no zero energy surface Andreev bound state. In the language of Majorana fermion, there is no Majorana fermion. On the other hand, if chemical potential is smaller than transfer integral, it's a topological phase, and we can expect zero energy surface Andreev bound state, namely Majorana fermion. Okay, so let's go to next chapter, next section. So we should mention about whether such kind of Majorana fermion is realized without using spin triplet superconductor, because spin triplet superconductor is very rare, and there's no good example up to now, definite example. Of course, there are many possibilities, but there is no definite example. So the question is that, is it possible to generate Andreev bound state, Majorana fermions, based on the conventional spin singlet S-wave superconductor? The answer is yes. So in that case, spin-orbit interaction is a key ingredient. How to use spin-orbit coupling? So there are several ideas. So Majorana edge mode, or flat band type, or chiral edge mode, helical edge type. There are several types of edge mode, several types of Majorana fermion has been studied. But all of these models, common thing is that we should consider spin-orbit coupling. So what is spin-orbit coupling? Let's start from this picture. So first we start from simple parabolic dispersion of free electron model. By introducing Rashba spin-orbit coupling, Fermi surface is split. And as seen from here, helicity of this Fermi surface and the inner Fermi surface are different to each other. And then if we apply Zeeman field, energy gap opens, and if we tune the chemical potential between this upper band and lower band, so the situation, only one Fermi surface exists. Actually, it's a really exotic metallic state, quite unusual metallic state. And if we put on pair potential here, then dramatic Fanning Cooper pair is possible. We can expect spin triplet P-wave-like state, not the exact spin triplet P wave, but spin triplet P wave-like state as far as we are looking at low energy excitation. So the story is as follows. This is a dispersion like that. This is a Rashba, only Rashba, and this is a Rashba plus Zeeman. So actually, following this idea, Roman Ruti and Yuval Oleg in Weizmann Institute has proposed very nice model. So the Hamiltonian proximity coupled to nanowire system. So it can be written like that. So it's a 4x4 BDG Hamiltonian. And the important point is that differently from my lecture today, in first part of lecture, we should consider carefully the structure of normal state. In that case, normal state Hamiltonian is not so simple, including Zeeman effect and also spin-orbit coupling. In that case, it's a one-dimensional. Only sigma 2 appears, k coupled to sigma 2. K is a momentum along x direction. So then, but it is impossible to get complete analytical solution. It's a little bit complicated problem. So let's first diagonalize, let's first diagonalize HK, and then the Hamiltonian becomes like that. Still, it's complicated. So then, focusing on the low energy band is possible by band splitting. Actually, this yellow marked region is relevant to low energy excitation. So then if we focus on these 4 terms, and then we first redefine the chemical potential from mu to mu plus A, and we get some constant, and then finally, the low energy effective Hamiltonian becomes like that. Strictly speaking, A is given this quantity. If we focus on only K is very small, then A is almost constant. Strictly speaking, it is not a P wave, but as far as we are focusing on very low K, then it can be regarded as effective spin triplet PX wave superconductor. So actually, I have explained in today's lecture, spin triplet PX wave superconductor, if it is realized, it's a really interesting stuff. So then we can expect very interesting nature in this system. So Asano-san is interested in this model. So he considered disordered segment attached to this nanowire. So this system can be regarded as a, designed PX wave system, as far as we are looking at low energy excitation, and calculate various quantity following my understanding of anomalous proximity effect. So then, in this model, when VZ satisfies this condition, so topological superconducting system is realized, it means that the effective triplet PX wave superconductor is realized. And actually, he has calculated in topological regime, he has checked that the existence of zero energy peak in local density state here. Okay, on the other hand, in non-topological regime, there is no zero energy peak. And similar anomalous proximity effect has been predicted in spin triplet P-wave continuous model in 2004 with Professor Kashiwaya. On the other hand, let's look at calculated conductance in nanowire. Only topological regime, it has a zero bias conductance peak. And the important point is that just at zero voltage, it's completely quantized. So similar anomalous charge transport has been clarified in diffusive normal metal attached to spin triplet P-wave superconductor. And actually we have checked that in topological regime, with the increase of air, this value is completely quantized. On the other hand, non-topological regime, it changes like that. So we can show that perfect resonance exists even in the localized regime numerically. And actually, we have already checked that for classical diffusive regime, we can show perfect resonance by exact solution of Usadel equation. Okay, so then let's look at another interesting system where Majorana fermion has a dispersion. So in that case, we call it chiral Majorana fermion. So there are several proposals up to now. Lianfu and Carl Benecke has done very similar work, where ferromagnet as S-wave superconductor is put it on surface of topological insulator. And also this system is a two-dimensional version of spin-orbit coupled system attached to S-wave superconductor and ferromagnet insulator. And also there are relevant systems. For example, quantum anomalous system coupled to S-wave superconductor, very interesting system. And also skyrmion lattice is coupled to spin singlet S-wave superconductor by Dr. Nakosai, who is working in a group now. Okay, so here the time is not so much. We'd like to focus on topological insulator junction problem. So let's start from what is topological insulator. Topological insulator is a special insulator which has a helical edge state. And so there is a non-zero topological number defined as a wave function and the helical Dirac cone as a surface state. What is helical Dirac cone? Helical Dirac cone is like that. So if we look at the above Fermi level, for example, complete spin momentum locking occurs like that. On the other hand, below Fermi level, the helicity is different to each other. So then let's start to put on some material, for example, ferromagnetic insulator or superconductor on the surface of topological insulator. Hamiltonian is like that, rather simple. So we start from surface state of topological insulator and chemical potential here and magnetization in this region and also pair potential here. And then we calculate that, for example, first we calculate charge conductance, system A. Then we get the answer that the energy level of Andreev bound state becomes like that. So it depends on angle theta, but how to say, momentum dependence, or how to say, theta dependence of Andreev bound state is quite similar to chiral P-wave superconductor. Okay, so if we choose mz equal mu, it becomes completely equivalent to chiral P-wave superconductor. One of the important messages that even without spin triplet P-wave pair potential, we can obtain essentially equivalent to surface Andreev bound states to that of chiral P-wave superconductor. This is an important point. And after some calculation, so the Andreev bound state becomes like that. Theta, horizontal axis corresponds to momentum prior to the surface interface. So it's a linear, almost linear dispersion. And also the charge conductance becomes like that. And it's similar to chiral P-wave. So here the induced Andreev bound state does not have a spin degree of freedom, only spin quenched. So Andreev bound state can be regarded as a chiral Majorana fermion. So this is a very interesting system. Okay, so then let's go to final part. So what is doped topological materials? I will briefly mention about that. So here, on the other, we look at doped topological insulator. In that case, exotic superconductor might be generated in doped topological insulator. For this purpose, we must consider the bulk Hamiltonian, minimal Hamiltonian of topological insulator. So we must prepare two orbitals like that, and also spin degree of freedom and particle hole, how to say, symmetry, particle hole space. So we must treat 8 by 8 matrix. But there are interesting material, so-called kappa doped bismuth to selen 3. So as regards this pair potential, Liang-Fu and Eretzberg proposed very interesting model. So they consider, although the momentum dependence is nothing, it seems to be S-wave, but as far as we write it in orbital basis, but there are quite exotic pairing because it is called orbital parity is odd. This means that Cooper pair is formed between two orbital, one orbital and two orbital. Here is one orbital and two orbital. So this pairing, these four types of pairings are interorbital pairing. And among these interorbital pairing, so delta 2 to delta 4 is topological pairing. This means that exotic surface state can be possible. Here we cut the surface for XY plane. In that case, delta 2 and delta 4 clearly shows a very interesting surface and F bound state. And the interesting point of this material is that original normal state Hamiltonian has a surface state. This surface state is of course nothing relevant to superconductivity, and actually it exists even in normal state. But this surface state still exists after doping, and also this state can survive due to strong momentum coupling depending on the type of Cooper pair. This is an interesting point. So let's briefly look at this nature. So actually the whole suggested pair potential has in some model, it's a gap-like structure, and in some model, has a, how to say, point-like node. So the density of state is proportional to E square for low energy. So then, let's look at the surface state charge transport problem in normal metal superconducting topological insulator junction. So delta 1, if we look at delta 1, and with the increase of Fermi surface mismatch, then charge conductance approaches like that. In some sense, it's similar to standard spin singlet S-wave pairing. Okay. On the other hand, delta 2 case is very different. In these cases, if we depending on the choice of chemical potential, if the resulting surface and F bound state becomes like that, in that case, the resulting charge conductance does not have a sharp zero bias peak because the contribution from zero energy is very small. So with the increase of barrier parameter, just at zero voltage, it has a dip-like structure, quite different from standard D-wave tunneling. On the other hand, by tuning the chemical potential, the, how to say, shape of F bound state dramatically changes. It becomes a caldera type momentum dependence, quite different. It strongly depends on the chemical potential. Also, similar thing occurs for pair potential delta 4. In this case, zero bias conductance peak exists, but the height of this pair potential, height of this zero bias conductance peak also depends on the chemical potential. So then we skip this one. Then why such kind of thing occurs? This is a nice explanation by Professor Yamakage in Nagoya University. He has carefully looked at the, how to say, F bound state by tuning the position of chemical potential. This green line is a, how to say, surface state, which exists even in normal state. Of course, it's a topological insulator. So doping means the chemical potential originally located between band gap, between this conduction band and, valence band and conduction band, it locates like that. Okay, so then if it's an overdoped material situation and chemical potential is located here, then we should expect such kind of cone type F bound state, and it does not produce sharp zero bias conductance peak. But if we change the position of chemical potential, and like here, very unusual thing occurs because in this interorbital pairing, it's strongly coupled to orbital spin locking. So then, impossible to gap out this point, and the dispersion of surface and F bound state becomes like that. Okay, so then, in that case, contribution from zero energy is large as compared to that one, then we should expect zero bias enhanced charge conductance. And there are famous experiment by Sasaki-san, which was when he was still in Osaka University more than 9 years before. He measured soft point contact spectroscopy and tin attached to kappa doped bismuth to selen 3 because kappa doped bismuth to selen 3 is a very, how to say, delicate material. Still, it is impossible to make a good junction. And they reported the existence of zero bias conductance peak. And after that, I have found one paper, niobium doped bismuth to selen 3. There's an experiment report from United States, Van Haringen's group, and they also reported that this material is relevant to topological material and might be possible. They mentioned P-wave pairing, but I think it's more natural to interpret based on Liang Hu and Eritz Berg's model, maybe delta 2 or delta 4 interorbital spin triplet pairing might be realized in this material. Okay, so I finished all of the contents. So I'd like to thank again for attendance and organizer Professor Golubov. Thank you very much.
Thank you, Professor Tanaka.
Are there any questions or comments?
Yes, please, who can ask questions? So you did actually a very nice overview. And well, maybe a general question.
Mm-hmm.
What do you think is the most promising type of junction with topological materials? What one can expect?
From experimental viewpoint or theoretical viewpoint?
Maybe from experimental viewpoint, indeed, yes. For realization of Majorana fermions, for example.
It's difficult to say. Actually, nanowire system is simple, but from experimental viewpoint, it is very difficult to fabricate a single channel idealistic situation. On the other hand, in edge state of microwave telluride is good because it's an edge state and nicely, how to say, controlled. Actually, in Würzburg's group. And I have a chance to read one doctor's thesis from Würzburg. His name is Fleckenstein. And he has calculated very nice idea for the interaction of helical edge mode. And actually, interaction with helical edge mode is possible making nano constriction. And maybe you know that if we put on 2 superconductors on helical edge mode, so we are now here, we are considering 3-dimensional and 2-dimensional surface state. But if there is a helical edge mode, 1-dimensional chain, 1-dimensional, how to say, edge mode, from our counter propagating spin up, spin down, and put on ferromagnet and superconductor, then it is possible to generate, how to say, Majorana fermion, actually zero energy, idealistic Majorana fermion. Maybe experimentally not so easy, but in Würzburg's idea is as follows: to nano constriction close to each other. So then we can gap out another reason. For example, Coulomb interaction. In that case, they comment that more exotic fermion is possible, so-called parafermion. Z4 parafermion might be possible. And actually, the existence of Coulomb interaction between 2 narrow nano constriction becomes possible, accessible now. And the experimental report of H/E square conductance from Würzburg. This is one of the possibilities. And another possibility is not so clear experiment, but it's experimentally possible. So Kashiwai-san's group has reported that magnetic doped topological insulator is possible. And if we put on superconductor on the magnetic doped topological insulator, then it is possible to generate chiral Majorana fermion rather easily. This is one of the, this is my answer.
Thank you. Thank you for your comments. Yeah, it's really very challenging subject. We have time for 1 or 2 short questions from anybody.
Summer school, we will have discussion and we can think about the possible experiments. Most important that this summer.
I'm sorry, I cannot hear.
Is your microphone on?
Yes, yes, yes. Are there any questions?
Tanaka-san, thank you very much for the very.
Okay, voice is a little bit, how to say, small. Could you please speak more loudly?
I try to do. A moment. I will. I will increase. Yeah. Okay. So.
Can you speak more loudly? I'm sorry.
Thank you very much, Tanaka-san, for very interesting and motivation of the experiment. And I believe that we can think about the possible experiment with constriction, because we have already done some Josephson contacts using ion focusing, myelin, and such small size constriction we can construct, and that's why we will discuss the possible experiment to detect Majorana fermion.
What kind of material are you doing now?
We did Josephson contact with ferromagnetic weak link using niobium as reservoir of copper pairs, usual S wave, and artificial multi-layered metamaterial, magnetic metamaterial as magnetic weak link. But using this smart technology, we can use another material, and we can discuss the proper material for preparing of such constriction using a conventional superconductor, as you told, and to create the system which you mentioned in Würzburg calculated.
So do you expect a strong spin-orbit coupling in your material? Strong spin-orbit coupling?
Yes, it is possible, yes. Yeah.
Oh, I see, I see. So my naive impression is that both spin-orbit coupling is very important to reduce the spin degree of freedom. And of course, presence of ferromagnet is very important. So how to experimentally accessible, how to say design experimentally accessible system where electrons' degree of freedom is quenched, reduced. So how to make a helical fermion system experimentally easily? This is an important point, I feel. Helical means a spin due to spin momentum locking. In standard electron system, of course, if we fix momentum k, there is an up spin and down spin. But if some kind of how to say special interaction exists, simultaneous existence of spin-orbit coupling and, for example, Zeeman field, then we can design very unusual situation, so-called anomalous metal. The strong spin momentum locking occurs. Momentum k only have up spin and momentum minus k only have down spin.
Okay, good. That's why we have the ideas for discussion and to think about the proper way for realization of such depressed freedom of electron movement. That's why I understand that a key idea is to realize the frozen freedom of the electron movement.
Yes.
Okay, good.
Okay, thank you very much. Okay.
Thank you very much, Tanaka-san.
Okay, thank you very much.
Thank you. Yes, in view of time, let's thank you again and close your presentation.
Okay, okay.
So we're a little bit out of schedule. So for Suzuki-san, I suggest to start in 5 minutes from now. Yeah.
Okay, okay.
5 minutes break.
In 5 minutes. Okay.
Is it okay? Yeah. In 5 minutes. Okay.
So superconductivity occurs at a low temperature. In the superconducting state, the resistivity of the material becomes 0. So in addition, the superconductor shows anomalous electromagnetic responses. So, and this superconductivity is caused by the Cooper pairs. And these Cooper pairs can be classified into roughly speaking, into the 2 symmetry classes. One is even frequency pair and the other is odd frequency pairs. So most of the studies so far have focused on the even frequency Cooper pairs. So, but in this talk, I will explain the odd frequency pair can also make interesting phenomena. So to define the odd frequency pairs, I have to show several formulas. So theoretically, the existence of the Cooper pair can be written in this pair function, which is basically anomalous Green's function. So pair function is defined by the product of 2 annihilation electron operators. And the electron is fermion, so these operators have to satisfy this anti-commutation relation. So combining these 2 formulas, we have this equation. This equation tells us when we exchange 2 electrons, the pair function must be antisymmetric. So the classification of the Cooper pair is based on the spin and the spatial coordinate. In this case, the pairing function is classified into 2 symmetry classes. One is spin singlet and even parity, or spin triplet or parity. And the superconductors discovered so far are classified into either of these 2 symmetry classes. However, this classification is true only for the order parameters, I mean the pair potentials. So let me show you some examples. So let us consider the diffusive normal metal superconductor junctions. In this case, the Cooper pair can penetrate into the diffusive normal metal. This phenomena is called proximity effect. So for example, in the D-wave superconductors, a Cooper pair penetrate into the diffusive normal metal. However, the diffusive normal metal is in the dirty limit, which means that only the isotropic S-wave pair can survive in the diffusive normal metal. So then we have a S-wave spin singlet Cooper pair in the diffusive normal metal. And this pair satisfies the antisymmetric relation. However, if we use P-wave superconductors, so we have spin triplet S-wave Cooper pairs. And this pair doesn't look like satisfy the antisymmetric relation. So what is the problem here? So simply we forgot one important degrees of freedom of electron. So electron has 3 degrees of freedom, spin and coordinate, and also time. So which means that Cooper pair also has time degrees of freedom, which means that the Cooper pair has a frequency degree of freedom. So we have to generalize the pairing function as shown here. So now we have to consider the time degree of freedom. So, and the pair function depends on the frequency. And the antisymmetric relation is also generalized as shown here. So we have to flip the frequency when we consider the antisymmetric relation. So in this case, the classification is also generalized into this as shown here. So now we have 1, 2, 3, 4 symmetric classes. And yeah, and these 2 symmetric classes is antisymmetric with respect to frequency. So they are so-called auto-frequency Cooper pairs. And now we can see that the spin triplet S-wave pairs should be auto-frequency Cooper pairs. And so far, yeah, and unfortunately, auto-frequency superconductivity have never been found yet. However, even when the superconductor is even frequency, the auto-frequency pair can appear as a subdominant component. So this is basically the basics of the auto-frequency pairs. And this auto-frequency pair is deeply related to the Andreeff bound states. So then first, so let us consider the pairing symmetry at the surface of the D-wave superconductor. So the pairing symmetry of the D-wave superconductor is, of course, spin singlet D-wave. However, at the surface, near the surface of the D-wave superconductor, inversion symmetry is locally broken. So which means that the parity is no longer a good quantum number. So, and near the surface, which means that near the surface, the pair function should be written as a superposition of these components. And it's very important, these P-wave singlet and F-wave singlet pair should be odd in time, should be odd frequency Cooper pairs. And yeah, and the amplitude of these odd frequency pairs is deeply related to the Andreeff bound state, because when there's an Andreeff bound state, the pair potential are suppressed at the surface, which means that the superconductivity is more inhomogeneous when there is an Andreeff bound state. So therefore, when there's an Andreeff bound state, these auto-frequency pair has the larger amplitude. Yes. So, and this is the basics of the auto-frequency pairs. And now let's move to what kind of phenomena auto-frequency pair can cause. So in 2005, Professor Tanaka studied the Meissner kernel of the auto-frequency pairs. Meissner kernel is corresponds to this part. Yeah. Yes. So, and they consider the junction shown here. So in this case, depending on the pairing symmetry of the superconductors, the odd frequency or even frequency Cooper pairs are induced. And this is a calculated Meissner kernel. The results, so yeah. So roughly speaking, when the even frequency pairs are induced in the diffusive normal metal, the Meissner kernel is positive as always. However, when the odd frequency pairs are induced, the Meissner kernel becomes negative. which means that the supercurrent carried by the odd frequency pair is opposite, flows opposite direction compared with even frequency pairs. And that this strange magnetic property can be detected by the surface impedance. In 2011, Asano-san considered this situation where the superconductor is covered by the diffusive normal metal, and the electromagnetic wave is irradiated to the surface of the diffusive normal metal. So, and they discussed the surface impedance. So surface impedance can be written like this. R is a surface resistance, X is a surface reactance. In this case, the relation between the R and X is only important here. So this is a result for the S-wave case. I mean, the even frequency pair is induced in the diffusive normal metal. So in this case, resistance is always smaller than the reactance. And this is very typical behavior of the surface impedance for superconductors. I mean that this is the usual response. However, if we use the P-wave superconductor, I mean that the odd frequency pair is induced in the diffusive normal metal. Yeah, the resistance has a peak, strange peak at the low temperature. And also the reactance changes its sign, corresponding temperature. And at some temperatures, and the reactance is smaller than the resistance. This is very unusual. And they said this is a signature of the odd frequency pairs. And also, yeah, and to understand this strange magnetic response, they analyze the effective pair density. So the effective pair density can be written like this. JE is now simply just tangent hyperbolic function. The Ks is the so-called spectral pair density. The Ks for even frequency is shown here. In this case, Ks has a large positive peak at finite energy. So which means that the pair density of the even frequency pair is positive. However, the spectral pair density for P-wave looks like this. There is a huge negative peak at low energy. So which means that the odd frequency pair has effectively negative pair density. So this is very interesting. And yeah, so which means that this relation means that odd frequency pair shows may show the opposite response to the external perturbations compared with even frequency pairs. Yeah, and this negative pair density can be applied to the spin susceptibility in the aerogel helium-3 B-phase junction. So roughly speaking, in this system can be regarded as a diffusive normal and a P-wave junction. So the system is shown here. So in 2013, Higashitani studied the spin susceptibility of this system. Yeah. And this is a pair potential. So you can see that the pair potential is suppressed in the diffusive normal metal. And correspondingly, odd frequency pair has the large amplitude in the diffusive normal metal. And this is the spin susceptibility. So at the bulk, the spin susceptibility is reduced. However, at the surface, the spin susceptibility is greatly enhanced. So this behavior can be understood by the negative pair density of the odd frequency pairs. So pair potential of the helium-3 B phase can be written like this, where D is D vector. So, and the D vector contains the Z component, which means that the Cooper pair has pair potential contains this opposite spin triplet. So in the normal state, where the particle can change the population of the spin without any restriction. So, and the spin susceptibility reaches at a certain value. However, in the superconducting state, so they have to form opposite spin Cooper pairs. So, which means that the spin susceptibility should be reduced by forming this opposite spin triplet. However, if we use this idea to odd frequency pairs, so this odd frequency pair like a response in the opposite way compared with even frequency pairs, which means that the spin susceptibility should be increased. So, and this is the results of the odd frequency pairings. Yeah, and also, this negative pair density can change even the Meissner effect. Meissner effect is the most fundamental property of the superconductors. So, yeah, combining London equation and the Maxwell equation, we can derive the Meissner effect. We can show that the superconductor shows the perfect diamagnetic response, perfect diamagnetism. However, the odd frequency pair has the negative pair density, which means that the London equation is modified as shown here. So which means that the supercurrent can flow in the opposite direction compared with the usual even frequency pairing case. So in this case, the supercurrent can enhance the external magnetic field. So which means that the odd frequency pair is like paramagnetic against the external field. So then we consider this kind of a two-dimensional small superconducting disk. In this case, radius is the order of the London penetration depth. And we consider the usual spin singlet S wave and the D wave, and also spin triplet P wave superconductors. So the results are shown here. This is a result for S wave superconductors. This is the local susceptibility. So blue means the usual diamagnetic response. So, and this is a current density. Of course, current density is diamagnetic. So this is just usual Meissner diamagnetic supercurrent. So yeah, we can get the results for the D-wave superconductors. In this case, at these four surfaces, we can see that we can find the anomalous paramagnetic response. And the current densities are shown here. At the center of the disk, the usual diamagnetic current flows. However, at the surface, we can see that the anomalous paramagnetic current flows. We also analyzed the pairing symmetry, pair function, the symmetry of the pair functions. And this is the D-wave component. So D-wave component is basically even frequency pairs. And this component has the same profile as that of the order parameters. And we also show the P-wave component. So in this case, P-wave component should have the odd frequency. So P-wave component is the odd frequency Cooper pairs. This odd frequency pair doesn't have an amplitude at the center of the disk. However, these four surfaces, it has a fairly large amplitude. And comparing these three figures, we can see that at the surface of the D-wave superconductor, the P-wave auto-frequency pairs are induced, and that carries a anomalous paramagnetic current. And due to this paramagnetic current, the superconductor can be even paramagnetic. Yes, so this is so-called the paramagnetic Meissner effect. So we also study the effect of the surface roughness on this paramagnetic Meissner effect. So because in real experiment, probably the surface of the sample is not so clean. So we have to check if the odd frequency pair is robust or fragile against the surface roughness. So again, this is a result for clean limit of the D-wave superconductor. At the four surfaces, we can see that the paramagnetic response. So if we introduce the surface roughness, the paramagnetic response completely gone. And this is a current density. We can see that the paramagnetic current carried by the P-wave odd frequency pair completely vanish. We can carry out the same simulation for spin triplet P-wave superconductors. And this is a local susceptibility in the clean limit. In this case, the supercurrent carried by the S-wave odd frequency pairs. Yes, then if we introduce the surface roughness, so yeah, surprisingly, the paramagnetic response still survive, still present. And yeah, and the supercurrent carried by the odd frequency pair is still present even under the surface roughness. And yeah, by integrating this local susceptibility, we can calculate the susceptibility of this superconducting disk. The results are shown here. This is a result for D-wave superconductor. This is a result for P-wave superconductors. And this parameter can change the strength of the surface roughness. So in the P-wave superconductor, they show the anomalous, unusual paramagnetic response at the low temperature when the surface roughness is weak. However, this paramagnetic response vanishes under the strong surface roughness. Yeah. On the other hand, the paramagnetic effect of the P-wave superconductor is quite robust against the surface roughness. So the difference between these two can be understood by the orbital part of the odd frequency pairs. In the D-wave superconductors, the induced odd frequency pair has the P-wave symmetry. So because P-wave is a anisotropic pairing, such an anisotropic pairing is basically very fragile against the impurity potentials. So as a result, the D-wave superconductor shows the usual diamagnetic response when the surface roughness is quite strong. However, on the other hand, the odd frequency pair induced in the P-wave superconductor has mainly the S-wave component, S-wave pairing symmetry. So S-wave pairing symmetry is isotropic, so which means this pair is quite robust against the impurities, the surface roughness. So as a result, even under the surface roughness, the P-wave superconductor can show the paramagnetic Meissner effect as shown here. Yeah. And this paramagnetic effect is actually observed a couple of times in experiments. This is an experiment in in 98. So they prepared a thin film of the YBCO, and using the ion bombardment technique, they cut this film into narrow superconductors. In this case, the surface can dominate the magnetic response. Now surface means like internal surface introduced by this ion beam. So the experimental results are shown here. So that usually, so this is a temperature and this is a penetration depth. Usually the magnetic penetration depth decreases monotonically with decreasing temperature. However, in this film, at a low temperature, the penetration depth slightly increases. So, and this is the results of this is due to the odd frequency Cooper pairs induced near the surfaces. Okay, yeah. So, yes. In the previous sections, I explained how to generate the odd frequency pairs by changing the orbital part of the Cooper pairs. However, we can also generate the odd frequency pairs by changing the spin structure of the Cooper pairs. So let us focus on this case. So let us first consider the superconductor and the ferromagnetic metal junction, as shown here. In this case, of course, the proximity effect occurs. The spin singlet S-wave Cooper pair can penetrate into the ferromagnet. However, there's a magnetization in the ferromagnet, which breaks the spin rotational symmetry, which means that the pair function in the ferromagnet can be written as a superposition between the superposition of the spin singlet S-wave and the spin triplet S-wave Cooper pairs. Now again, this spin triplet S-wave should be even frequency pairs. Yeah, and but actually this has kind of problem because this odd frequency pair, spin triplet odd frequency pair, cannot penetrate in a long distance into the ferromagnet. So the penetration depth of the proximity effect is based in the usual case, in the usual SN junction. The penetration depth is characterized by this psi n. This is under coherence length. However, in the SF junction, the penetration depth for this S-wave spin triplet is characterized by the psi n. This is much shorter than the psi n. Yeah, psi n. Yeah, but however, by introducing another layer of the ferromagnet, where the magnetization directs the different direction of this magnetization, we can generate the equal spin triplet. And in this case, it is well known that this equal spin triplet can penetrate with the order of this psi n. So, since this Cooper pair has the spin degree of freedom, so this equal spin triplet pair is expected to be applied for so-called superconducting spintronics. In this case, so the current is carried by the supercurrent, which means not dissipative, and the Cooper pair can carry the angular momentum. Yes, and this spin triplet S-wave component is odd frequency, so which means that they show the anomalous magnetic response. And this is the theoretical work by the Sasha Golubov. And they consider that this kind of system, SF junction with a vortex. So if there is a vortex, the screening current have to flow around the vortex. But they found that depending on these parameters, the supercurrent can flip the direction, which means that, yeah, I think so this is no longer screening current. This current can enhance the vortex, enhance the magnetic field of the vortex. Yes, and actually the paramagnetic effect by this spin triplet S-wave component is experimentally observed. So yeah, this is an experimental work by Bernardo. So they made a junction shown here. So where they use the holmium instead of the ferromagnet. So holmium is a conical magnet where the magnetization has this kind of spiral structure. This collinear magnetization can generate the spin triplet auto frequency pair in the gold. And using the low energy muon spin rotation technique, they measure the local magnetic field in the junctions. The experimental results are shown here. This axis means the depth, and this axis means the local magnetic field. Then, as you can see, that below the superconducting temperature of the niobium, the external field is enhanced in the gold layer and the screen in the niobium layer. So yeah, and this enhancement is this is the paramagnetic, this is the result of the paramagnetic Meissner effect. So now we can see that the paramagnetic response is really exist and can be measured by the experiment. And yeah, and this year, another experiment is carried out. So yeah, this is so they consider the junction of the topological insulator and the superconductors. And as a topological insulator, they used bismuth-2 selenide. And as a superconductor, they used a niobium. So, and as Tanaka sensei explained in the previous talk, so this topological insulator has the two orbital. So in this case, the proximity effect is also slightly tricky. In the superconductor, the Cooper pair has spin singlet, S-wave, even frequency pairs. So, however, in the bismuth selenide, so we have to consider the band degree of freedom. So in this case, we can induce the spin singlet, S-wave, odd orbital, and odd frequency Cooper pairs. So this is slightly tricky, but we can induce the odd frequency pairs. So the experimental results are shown here. Yeah, and you can see that in the bismuth selenide, the external magnetic field is slightly increased. So under this, so they conclude that this is the evidence, this is the signature of the odd frequency Cooper pairs. Yeah. Yes. Yeah. Then let's move to our recent works. So recently studied the inverse proximity, the relation between the inverse proximity effect and the odd frequency pairs. So let me first explain what is inverse proximity effect. So if we consider the ferromagnet and the junction of the ferromagnet and the superconductor, the usual proximity effect occurs. The Cooper pair can penetrate into the ferromagnet. So however, at the same time, the magnetization in the ferromagnet can penetrate into the superconductor. And the length scale of this inverse proximity effect is characterized by the superconducting coherence length. So which means that this phenomena is related to the superconductors. The origin of this phenomena is the superconductivity. So far, so inverse proximity effect in the several cases have been studied. So, but actually there are only 3 cases. Yeah. So in these 2 cases are ballistic, and this case is diffusive. And this case uses ferromagnetic insulator, and this case uses the ferromagnetic metals. So, and interestingly, depending on the situation, the direction of the induced magnetization changes. So the motivation of this work is rather simple. So the usual proximity effect is greatly changed by is really depend on the pairing symmetry of the superconductors. So what about the inverse proximity effect? So in the for example, in the P-wave superconductor, there is an unbound state at the interface. So that may change the direction of the induced magnetization. Okay, so then we calculate the magnetization of the inverse proximity effect. This is a result for in the 1D limit. Yeah, the induced magnetization for S-wave superconductor is always parallel. It means that the magnetization of in the ferromagnet and the induced magnetizations are always parallel. Yes. On the other hand, if we use the P-wave superconductor, the magnetization is inverted. The direction of the magnetization is opposite. So under this is the temperature dependence of the induced magnetization. We can also calculate that the M0 dependence of the magnetization. Now M0 is the magnetization in the ferromagnet. This is a result. So we can see that the magnetization induced in the P-wave superconductor is always opposite to the S-wave superconductors. And also, at the same time, in both cases, the induced magnetization change its direction with increasing M0. So, we found that this direction of the magnetization is determined by the scattering spin mixing angle. So in the FS junction, the reflection coefficient depends on the spin, depends on the injected spin. So in this case, the reflection coefficient has an additional phase depending on the spin. So the spin mixing angle can be defined by the phase difference of these 2 reflection coefficients. So under these 2 results tells us that the direction of the induced magnetization is determined by the 2 factors. One is the pairing symmetry, and the other is the sign of the spin mixing angle. Okay, so under this result is actually valid also for ferromagnetic insulator junctions, where there's no Fermi surface in the ferromagnetic insulator. So this is a result. again, the induced magnetization for P-wave superconductor is always opposite to the S-wave one. And this result can be extended to the two-dimensional system. The results are shown here. So we can see that the results for Px and dxy is always opposite to the usual S-wave superconductors. So in these two cases, actually the surface unrefound state appears. So which means that the direction of the magnetization, induced magnetization, is determined by whether the unrefound state exists, and also the sign of the spin mixing angle. So let me summarize. So let me show the summary slide, and let me stop. And that's all of my talk. Thank you very much.
Okay, thank you very much for your nice talk. So we have time for some questions. Somebody, I have a question actually regarding your last part about
inverse proximity effect.
Inverse proximity effect, yes. About the sign of magnetization. Is it any, maybe, I guess it should be some very simple explanation of why the sign is opposite. So sign in P wave case and S wave case.
Yeah, actually, so actually it's not so simple. So yeah, that is so we try to analyze the pairing symmetry at the interface. So basically, the magnetization is created by the product of the spin singlet and triplet pairs. And in the S-wave case, in the S-wave junction, so dominant component is a spin singlet S-wave. Spin singlet S-wave. I mean the even frequency pairs. On the other hand, if we use the P-wave superconductor, the dominant component is the spin triplet S-wave. So we can show that these two cases, the generated magnetization should be opposite. So this is a reason, like the dominant component is different.
Okay, thank you.
Yep.
More questions or comments? So if not, I think I would like to thank again both lecturers of today, Professor Tanaka and Dr. Suzuki, and also all the speakers from yesterday. We had, I think we had very nice school, very interesting information. To remind you, all these talks are recorded, and you will receive a link very soon where everybody can download all the lectures. Okay, Anatoly wants also to make an announcement. Yeah, please. Okay, please do.
Dear colleagues, yesterday Professor Nikolai Klyonov sent us information that he is the invited editor of the special volume Journal of Symmetry, impact factor something like 3. It is first quartile journal, and he invited participants and lecturers and colleagues to submit articles. Deadline, I believe, March 2021. We have already good tradition. After last summer school in September last year, I was invited editor of Beilstein, Journal of Nanotechnology. And now this is volume number 11 is printed, and excellent articles of our participants of summer school in Kishinev are already published. And we can continue this tradition, and we invite you to submit your articles.
The information will be on the website? Yeah.
We will send to all participants email with a link to this journal, with information from Professor Klyonov, and link to this journal, okay? And once again, thank you all very much for intensive work and 2 days brainstorm in our area of investigation.
So goodbye to everybody.
Goodbye. Goodbye.
Okay. Thank you for participation.
Thank you very much.